Hey, Honors Chemers. Today's podcast is hopefully going to be a very short one because this should be a review. We're going to go over direct and inverse relationships, which you've studied lots and lots in your math class. But this will be kind of applying it to science situations. It's basically the same thing though. The first thing we're going to talk about is a direct relationship. A graph for a direct relationship might look something like this, where as you increase the x value, the y value also increases, so it has a positive slope. Here's a couple other ways that we could say something has a direct relationship. You could say when one value increases, when one variable increases, so does the other. Or you could say that the line of best fit for the data is linear. It's a straight line. You could say that x is directly proportional to y. You could write it as you do in math, where y equals m, the slope, times x. But in science, we like to have the variables on one side together, both x and y on one side, and set it equal to a constant. So what we did is divided both sides by x, so that x and x cancel out over here. So y over x equals a constant. So this is the way we're going to represent relationships in science. On the other hand, an inverse relationship has a graph that looks more like half of a parabola. And as you increase along the x-axis, the y value decreases. So you could say the line of best fit looks like half of a hyperbola. You could say that as one variable increases, the other one decreases. You could say that x is proportional to 1 over y, or y is proportional to 1 over x, as you would in math. But in science, remember, we like to have, oh wait, I think that might be backwards. Oh, nope, here we go. Mathematically, that's what you would write. Y equals k over x, my bad. And then in science class, we'll actually show the variables on the same side equaling the constant. So we'll multiply both sides by x, so that x over here and x over here cancel out. So x times y is a constant. So a lot of people get confused because you may have memorized that inverse means there's a divided by sign in the equation. No longer is that true, although it's basically saying the same thing. Now you're going to see an inverse relationship as the two variables, x and y, or v and p, or whatever the variables are, as being multiplied together. That represents an inverse relationship. Okay, great. Let's try a couple practice examples and see if you can identify whether they're direct or inverse. So let's take a rectangle where one side always has to be 5 centimeters, and we can change the other side. How does the value of the area change as you increase the length of that side? Well, remember, area is length times width. So if the changeable length is 5 times 5 to get the area would be 25. 5, the fixed side, times 10, if the length was 10, would be 50. 5 times 15 would be, oops, I don't know how to do that. 5 times 15. Ooh, baby, I need to bust out that calculator. That's going to be 75. 5 times 20, that's 100. Wow, I just had a little mental math break there. That's kind of sad. And then 5 times 25 would be 125. And you know what? I think I had those numbers written in there already. Let's make sure we got those right. Excellent. Okay, and then when you graph the data of length of side, x, by the area, your y value, you see that you get this nice linear line. Now, in science, our data is never going to be quite that perfect. But if generally when you draw the best fit line, it looks like a straight line, then you say that the relationship is direct. That is a direct relationship between length and area. As one increases, so does the other. Okay, and here's another example. Let's consider the pressure exerted on a person. Yes, we have this poor little person here. We're going to try to put a weight on his head that has a force of 20 newtons. What's going to hurt worse, do you think? If the surface area is small, like the head of a pin, or if the surface area on his head is large, like a piece of wood with the weight on top of it? Obviously, the pin's going to hurt a lot more because all the pressure of the weight is centered on just one tiny part of his head. Poor little guy, he's going to get crushed. Well, let's mathematically prove that. If pressure is the force exerted over a certain amount of area, let's calculate the pressure in each of these cases. Well, if the area is 0.1 and the force stays constant at 20 newtons, 20 divided by 0.1 turns out to be 200. And then I'll just calculate those values for you real quick. There you go. Okay, why don't you try to graph that data on your own and see what it looks like. Hopefully eventually you'll see that the data will look something like this. And when you add a line of best fit, it is definitely not a straight line. It is more like a half of a hyperbola. Therefore, the relationship is inverse. So we mathematically proved that pressure and area have an inverse relationship. Doesn't help the guy who just got squashed though, unfortunately. Okay folks, that's really all there is to it. So just make sure, can you do these things? Can you identify whether any two variables have a direct or inverse relationship based on their equation in this form? So take a minute, write down your notes. Identify which of those equations is which. Could you identify direct or inverse based on experimental data? So as one variable increases, the other decreases. That's which relationship. As one increases, the other increases. That's what kind of relationship. And then finally, based on their graphs. So if you have those things written down, you got those down, you are good to go. You are ready for our It's a Gas activity. Looking forward to seeing you then.